All right. So, in the previous class, we have done the mathematical portion of logistic regression, and today I am going to show the codes or implementation of logistic regression. Before that, again, I want to show you the value of parameter optimization. That's what we have calculated. Delta cost function upon delta beta naught, that was equal to h theta x minus 2y, and delta cost function delta beta 1 was equal to h theta x minus 2y. We do have x also here. Okay, so these were the value of the differentiation which we have performed for beta naught and beta 1. Now I want to tell you something, that obviously we have to update the value of parameters beta naught and beta 1. We are looking forward for optimal parameters so that the errors should be reduced. Okay, that's what we are looking forward for. Because you very well know, in case of logistic regression, we have to find the probability. Okay, that is P, that is our prediction H theta x. And this prediction, the probability, is equal to 1 upon 1 plus e की power minus beta naught plus beta 1 x. You already know about this thing. And I should have the optimal value of beta naught and beta 1. Then only I can get probability P, the best probability, which will define your outcomes. Okay. So we do have a formula, or I would say it's like an optimization equation, where basically it's used in deep learning. Okay, we study this thing in deep learning, and here it's written as w dash is equal to w minus alpha del L by del w. This equation is used in deep learning for optimization, where w is a parameter. It is also called as weight of a neuron. Okay, weight assigned to the neuron, that defines the strength of interconnection between the two neurons. In neural network, we do have layers, and in layers we are having neurons. Okay, that's how we make a neural network. Okay, fine. And this is how you give the input. Every neuron is connected to every other neuron in the layer. So the parameters for the neuron are weight and the bias. These two things are there. In context to that, because neuron also follow linear equation for its computation. Here x is given as an input, w is the weight, b is the bias, the output is y, which is given as wx plus b. The output is wx plus b. Similarly, if you check our equation here, you can say your probability is given as 1 upon 1 plus e ki power minus y. That is your sigmoid. Okay. And the value of y is beta naught plus beta 1 x. And there is a resemblance between these two. You can see. Fine. So, in optimization, deep learning, we have to adjust the weight using this equation. Okay, where alpha is the learning rate, that is also called as step size. Okay, that means I need to perform gradient descent. Okay, I need to find the minima. This is how I will move, and my goal is to find the minimum point, so that the error will be reduced or minimized. So with what rate you will perform your journey to find the minima, that is given by learning rate. It is called as a step size. Okay, we always keep the learning rate small because we don't want to directly jump towards the minimum. This is not possible. We have to make our model to learn. We want to make our model to get trained. For training purpose, we have to take steps, then only we can reach to the minimum point. Okay, if you keep high learning rate, then the high learning rate will fluctuate your gradients. Okay, the gradients will fluctuate and you will get wrong values for the weights. My goal is to update the weight. My goal is to update the parameter. For that, the update should be not uneven. Like initially, if my weight is 10, the parameter value is 10, my updated weight should be like 10.2, and so on. There should be you like, I would say, not uniform, not regular, but the update should be not like any kind of value which show according to the gradient exploding or vanishing. Exploding means high values of the gradient. Vanishing means tend to zero. So I want the updates to be like slowly the adjustment of the parameter has been done and we are reaching to the minimum. We never perform this thing. Okay, fine. Now let me share my entire screen, and it's very important concept because this concept is follow up in deep learning also. Okay, so why I told you this thing? Just again refer to this equation. I told we want to update the parameter. Okay, this is how parameter are updated. Alpha, I told you, that is the learning rate. L is the loss or error. And obviously, we want to differentiate. That's what we did now. We differentiate loss or error with respect to parameter. So that's what I did. Okay, in the equations which you have solved logistic regression, there also you did the same thing. Cost function or loss, na, it's like same, na. So that's what you did. One you have differentiated with beta naught, one you have differentiated with beta 1. That's what you have done. So same thing here also. So if I want to get the optimal values of beta naught by keeping this equation as a reference, I can write like this. Beta naught dash is equal to beta naught minus alpha del L by del beta naught. That is what I can write. Okay. So this will be updated value of beta naught, beta 0. Now, as I already know that the value of del L by del beta naught is given by h theta x minus 2y. That is already known to us. Now, for all the values of x, that means if you are having m features or m parameters present in the data set, so you can write like this. Beta naught is equal to, sorry, beta naught dash is equal to beta naught minus alpha summation of I equal to 1 to m h theta xi minus 2yi. That's what you can write. This is the update equation for beta naught. Okay, similarly, you can write the update equation for beta 1 also. Beta 1 dash is equal to beta 1 minus del alpha del L by del beta 1. Remember, in the equation, y minus sign is present because we do calculate gradient descent. Descent means, okay, you have to go down. Actually, the direction of gradient that's been assumed to be in upward like this. Descent means opposite to the direction. So, in order to take opposite direction, we keep minus sign. Okay, so this is gradient. Minus means descent because you need to find the minima. Okay, so to get the minimum value, you have to put the minus sign. Okay, got it. Very important thing. I do talk about the basics, whatever be the necessary basics we require to understand any concept. I am covering that. Y minus sign, y plus sign, and each and every term I am explaining. Okay. So here also beta 1 dash equal to beta 1 minus alpha del L by del beta 1. Okay. Now you can substitute the value of del L by del beta 1, that will be your h theta x minus 2y, and x is in multiplication. Then you can take for all the data points. So that means your I equal to 1 to m. Okay, so it will be like summation I equal to 1 to m h theta x I minus 2y I and xi. That's what you can take. Okay, fine. So this is the updated equation for beta 1. This is how you are going to find the coefficient. This is how you are going to optimize your equation. Fine. So whatever I have taught in these 2 days, it's all related to optimization. Okay. So here yi is actual value. Xi is your, okay, this is a feature value. Okay, this is feature value, data point. Okay, h theta xi is predicted. H theta xi is predicted value. Okay, got it. Fine. So if you are having m data points, okay, don't say. I think I have above I told m features. Okay, here m are the number of data points you are having. So assume this thing like, just assume like this. You are having, okay, this is your data. Okay, and this is x1, x2, x3, x4, x5. Okay, and this is your actual, and this is your predicted. Okay, so actual is y, predicted is h theta x. Okay, fine. So predicted minus actual. So whatever be this value minus this value, that will be the error. Okay, that will be error. And over what value of x we are calculating this difference, that is your xi. Okay, fine. So this is what the rest of the maths for the logistic regression. Okay, fine. Now let's check the implementation of logistic regression, how we do how we use it, logistic regression. So NumPy, Pandas, basic library. You are taking data set from sklearn, train test split to train test splitting of your data. And here is your model, logistic regression. So logistic regression is present in linear model only. Okay, so linear regression is also present in linear model. Logistic regression is also present in linear model. But you very well know what is the task of logistic regression. It's a classification algorithm. Okay, and the rest are the evaluation, accuracy score, confusion matrix, classification report. These are for evaluation to find whether your model performed well or not. Okay, so this is the classification report and confusion matrix, accuracy score. Okay, then the next are the visualizations. Okay, your Seaborn and the Matplotlib, these are the visualization libraries. Okay, I took my data from the sklearn only. I am not taking any specific data set. No, I am taking the data set which is already present in sklearn. Okay, so sklearn or scikit-learn, both are same. Okay, just consider them as same. These are the base libraries specially for machine learning. In sklearn or scikit-learn only, we are available with linear model, and in linear model we are available with linear regression, we are available with logistic regression. Okay, so this is my base, and then I am having sub directory. So let's consider this is your directory, this is your sub directory, and these are the files or the libraries. Okay, these are the libraries which are present in this subdirectory. Okay, so in library we do have a code how to implement linear regression or logistic regression. It comprises of the code, the algorithm. Okay, how to implement these regression we are having. So we are importing that. Okay, and in sklearn datasets, sklearn also have the datasets. Okay, from it is having many datasets. I am taking iris data. Iris is a flower data. It's a standard data which is present in sklearn. It's a benchmark data, you can say, which can be used for trial purpose. Okay, so it's a flower data set, and it's used for classification because we are having three classes. You are having three classes present in iris. Okay, so I am taking this particular data set. Okay, this is my feature, this is my target. All right, and then I create a data frame using the features which I took from above from iris data, and this is my target. So df is my data frame, and I printed the data frame also. Head, first five rows of the data set I printed. Then I performed train test split. Okay, that means test size I took 20%, training size I took 80%. Okay, random state 42 means as many as times I run this code, doesn't matter. Whatever be the splitting has been performed here, that will remain the same. That is why random state 42. Here I am taking my logistic regression model. Okay, maximum iteration 200. That means okay, as I told na, that in logistic regression we have to find the value of parameters beta naught and beta 1, optimal value of them. So there I have mentioned that 200 times you can iterate. Okay, you can find, you try keep on finding the optimal value of beta naught and beta 1 following this equation. Beta naught dash is equal to beta naught minus alpha del L by del beta naught, and same for this thing also. Okay, keep on iterating for 200 times. Iterate or epo. Find the optimal value. Okay, it's up to you how many times you want to iterate. Okay, sometimes I give 1000 and something like that, such values. Okay, it depends. That will explore more when we will be talking about the hyperparameters of logistic regression. Okay, so I use logistic regression here and I put my data X train and Y train into the logistic regression to fit. Okay, fine. And it will calculate the probability. From here, model get trained, and I'm giving the test data to the model for prediction. And here I'm calculating the accuracy score. Okay, accuracy score. I'm comparing Y test and Y prediction. Okay, so you will train your model, you will find the prediction, and then after getting the prediction for accuracy, there will be comparison. This is X test over X test only. Okay, this is Y test and this is Y prediction. Using X test only, you have obtained value of Y prediction by putting this value of X test into model dot predict. So Y test is already there. Prediction you found using the trained model. Okay. And let us suppose the results are something like that: 1 0 1 0 1 1. These are the values of Y test. And let us suppose the predictions you are getting: 1 0 1 0 0 1. So you can see that, okay, this is also fine, this is also fine, this is also, this also. Here, there is a misclassification. The actual is 1, but the model predicted it as 0. So, model confused here. Okay, model confused. So, in total, one, 2, 3, 4, 5, 6. Total 6 predictions we performed. In 5 predictions, model gave the correct answer. Okay, so 2 threes are 6, 2 fifties are, and then 3 ones are 3, 3 6 are 18. Okay, and then again 2, and you are getting, and 3.666. Okay, 1.6. Okay, let's take 1.67 and multiply 50 with 1.67. Whatever be the result you are getting, that is the accuracy of the model. Okay, this is how accuracy is calculated. See, you have to sit, you have to listen to me properly and prepare the notes. Every concept here, what's written in the code, also I am explaining. Everything I'm explaining. So, first you train your model. What do you mean by training of the model? The training of the model means to find the optimal value of parameters, beta naught and beta 1. That's what you are doing now. There is no other meaning of training. Training means itself only this: find the optimal value of parameters. And once you got, you can use that equation to find the prediction. And then you can calculate the accuracy score, confusion matrix, classification report. I will be telling more about this confusion matrix and the classification report. Okay, anyways, here I am printing everything, and here I am making the plot for confusion matrix also. So this is your data frame. In Iris, let me tell you one more thing. Okay, let me talk about Iris data. In Iris data set, which is already present in sklearn, you are having the features as sepal length, petal length, sepal width, petal width. Okay, sepal and petal. In flower now, we do have sepal and petal. Okay, so length and the width. Okay, so sepal width, petal length, petal width in centimeter. So you can see these are the lengths which are available for the flower. This is your target 0 1. Okay, fine. So this will be the target. Okay, fine. So overall, it will be your data, Iris data. All the features do have continuous values. You can see in point. All the values are in point, fractions. 5.1, 4.94 centimeter, 3.5, 3.0, 3. All are in just point. So it's a continuous distribution. Okay. And the target is like we are having three types of flowers in Iris, three classes. That is Setosa, Versi, Versicolor, and Virginica. Setosa, Versicolor, and Virginica. You can take like, okay, this is class 0, this is class 1, this is class 2. So we will be having something like that. We'll be having a data like something this. So you should be knowing what is series, what feature it do have, okay, and what is the target, that you should be knowing. Okay, fine. Now, so we have performed the classification here using logistic regression. Okay, and you can see I'm getting accuracy of 100%. See, this data is very small. It's just for testing purpose. ठीक है, it's just for testing purpose. Here you are getting 100% accuracy. Okay, the model predicted everything correct. This is the confusion matrix for it. Okay, Setosa, Versicolor, Virginica. So model predicted everything fine. Okay, I used logistic regression again. Okay, the same code I applied. Okay, the thing is, here I made a decision boundary. Okay, I made a decision boundary because I taught in the previous class also that every classification algorithm do make do build a decision boundary. Okay, fine. So here you can see three classes. This is how they are distributed. Okay, sepal length and sepal width. Between these two, a plot has been made between training and the testing data. Sepal width and the sepal length. Three colors you are seeing, these three colors belong to the three flowers. Okay. And what you have done here, see the entire code is same. The all the libraries I imported. Data I took Iris. This is your Iris data I took. I performed train test splitting. I trained my model. I performed the prediction. And then here I have printed the accuracy also. So it's all same. The thing is, here I'm making decision boundary. So what are the x and the y, x values and the y values? Minimum of x, minimum of your y, and max of x and max of y. Okay, that's what I'm taking. And this is x colon 0, that means feature number 1. 0 means feature number 1. So minimum value of the feature number 1, maximum value of the feature number 1. Here also I am taking y minimum. Okay, this is for, okay, this is x colon minus 1 minimum. 1. 1 means feature number 2. And this is also feature number 2 max value. Remember, x colon comma 0 means take all the rows. If you want to show me, I can, here only I can show. This is column number 0, this is column number 1, this is column number 2, this is column number 4, this is column number 4. Okay, this is row number 0, this is row number 1, this is row number 2. So if I write x colon comma 0, it means that consider all the rows of column number 0. So this is column and this is row. That's what you have written there. See what you have written. X colon 0. That means all the row values of column 0. And here you are taking the minimum and here you're taking the max. Okay, because the first one I want to keep on x axis and the another one I want to keep on the y axis. Okay, so I will be keeping one feature, that is the zeroth feature, on x axis and one feature on the y axis. What is zeroth feature? You can see in the data. The zeroth feature, what you can see here is, okay, this is sepal length. The first feature is sepal length. One feature is sepal width. Okay, so that's what I think we are considering. Here you can see sepal length and sepal width. Okay, got it. So sepal length, sepal width. Fine. And then what you are doing in the code next, you are creating a mesh. You are creating a mesh grid. Like, okay, mesh grid is something like this. Okay, this is a mesh grid. Okay, like this. Okay, fine. Something you are doing. And then what happens is model.predict. Then you are performing the prediction. X dot ravel, y dot ravel. That means flat. Flat the values of what is x. Whatever be the values which are coming in between minimum to maximum of x, keeping a distance of 0.01. Okay, so whatever be the minimum of x, whatever be, okay, so let us suppose x min is 0, x max is 6. So here I have mentioned what x min x max 0.01. 0.01 means, okay, you have to take 0.0101 gap. So x min is 0, x max is 6. Next point will be 0.01. Next point will be 0.02. Next point will be 0.03 till here. Okay, that is how you are going to take. Okay, fine. So that's what mentioned, and then you have to put those values into the model for prediction, and then you have to draw it. So xx I am drawing, prediction I am drawing. I'm taking all these 3 points on the contour. I'm just making a contour plot. And the three classes, the Z will be the three classes. Now, this is the prediction. And the prediction will be Setosa, versicolor, or virginica, three classes. So I'm marking them with red, green, and blue. Three colors I'm marking them. Okay, and here I'm plotting feature number 0 and 1. Okay, feature number X train, feature 0, feature 1 for the training data, and here with the testing data. Okay, marking them with O and S. Okay, so train purple color and test is green color. Okay, something that's what you can see. Okay, so that's an explanation of the code. It's not hard and fast, it's a very simple Python programming. But only the thing is, I want to show you the decision boundary also. This is the decision boundary. We made a boundary for classifying the data points into three classes: Setosa, versicolor, virginica. You can see this purple, green, and yellow. Okay, so this sepal width, sepal length are divided into three classes. Okay, so these data points are coming in the region of the red region. It's coming in the green. These are the points are coming in the green region. These points are coming in the blue region. So these three region are the three classes. Okay, the regions are you are having. Okay, this is your, let us suppose, logistic regression, and let me again show you. Okay, this is how the regions are defined. Okay, so something like this. Okay, we can have like this. So this is green region, for example, and another are the regions which are mentioned like green, red, and blue, something like that. Okay, you can make green, red, and blue. These are the three regions, three classes: Setosa, versicolor, virginica, and these are the respective points which are coming in the regions. Okay, so there are some test and train points which are coming in red region. Some are the training points which are coming entirely in the green region, and these are the points which are coming in the blue region. Okay, so and these are the decision boundary which are separating them according to the region. Okay, got it. So two codes I have shown you, and you have to think over it. What is been mentioned here? What discussion is going on? Okay, code explanation is not something that's not the concern. My major concern. My major concern is a concept. My major concern is the maths behind each and every algorithm. What solution it is giving you, how you are treating the data. Rest is making the code and showing the result. That is something you can practice. I will share these codes with you. You can run the code, and then you can also look out for the terms what are mentioned. Okay, so not so much difficult. You can do that. Okay, so these two codes. Fine. I do have other codes also. I took other data set like wine data set for the classification. Then I took your breast cancer data also for the classification, and then here I took, okay, digit classification data also. So such kind of data sets I have taken. And then here are the technical terms like evaluation criteria. So these I will explain you in the another class. Okay, my next class will be based upon all these things. I will explain. Fine. And then we'll wind up our logistic regression. All right. Fine. So these are the concepts which I want to explain in today's class. Okay. So let me stop presenting.